Look closely at this drop. A heavy, dark purple liquid hits a clear surface, diffuses, and completely vanishes. Today, we are performing a complete oxidation to convert ethanol into ethanoic acid, using the reaction's changing appearance to monitor our progress. This checklist covers our starting materials. Safety goggles and gloves are required. We will use a test tube containing 3 milliliters of ethanol, a dropper bottle of 5% alkaline potassium permanganate, and a warm water bath. Molecules are invisible to the naked eye. Tracking exactly when and why these liquids change color is how we verify that a chemical transformation has successfully taken place. We begin at the bench by measuring the exact volume of our starting material. Transfer exactly 3 milliliters of clear ethanol into a standard glass test tube. Lower the test tube into the water bath. The water level outside the tube should sit just above the level of the liquid inside.
Firm warning tone. Never apply a direct open flame to the test tube. Ethanol is highly flammable, and a direct flame poses a severe fire risk. The water bath itself requires strict temperature control. Keep the water gently warmed, well below an active boil. Ethanol has a low boiling point. Excessive heat will evaporate the reactant out of the tube before any chemical conversion can occur. Dialing in this precise thermal control secures the environment, so the oxidation reaction can proceed safely. With the ethanol gently warmed, we bring in our oxidizing agent, the 5% alkaline potassium permanganate solution. We must introduce the solution slowly. Add it strictly 1 drop at a time. Watch as the first drop enters the heated ethanol. It swirls dynamically and within seconds turns completely transparent. Squeezing the entire dropper in at once is a common operational mistake. It turns the whole tube dark immediately, masking this intermediate phase and creating the impression of a failed reaction. During this transparent phase, the oxidizing agent is hard at work, actively donating oxygen molecules to the ethanol structure. This chemical reduction powers the change, moving from MnO4- to Mn2+. The permanganate ion is consumed, reducing to a manganese ion. This specific shift is why the deep purple hue vanishes. That disappearing color is real-time proof that the ethanol is actively consuming the oxidizing agent and changing its molecular identity. Continue the slow drop-by-drop addition of potassium permanganate, keeping a close eye on the liquid's clarity. You will hit a visual threshold. 1 final drop will enter the solution, and the liquid will stop clearing, taking on a permanent violet hue. This side-by-side comparison contrasts the 2 stages. Left, the active phase with a clear liquid. Right, the completed phase displaying a persistent, vivid purple liquid. That persistent color tells us that 100% of the ethanol has been successfully oxidized into ethanoic acid. The color remains because the ethanol is entirely gone. There is no reducing agent left in the tube to decolorize the newly added drops. This equation defines the entire physical process observed in the test tube, mapping the shift from CH3CH2OH to CH3COOH. The text over the reaction arrow identifies the environmental requirements: alkaline potassium permanganate and heat. On the right side sits our final product, the newly formed carboxylic acid. The stubborn purple color in your test tube is the definitive signal that the chemical conversion from alcohol to acid has reached total completion. The reaction is finished. The test tube now holds a stable, bright purple liquid, confirming your successful synthesis. Strong oxidizing agents like alkaline potassium permanganate or acidified potassium dichromate serve as universal laboratory standards for upgrading alcohols into carboxylic acids. Before leaving the bench, safely dispose of the oxidized chemical waste in accordance with strict laboratory environmental guidelines. Mastering these precise visual indicators gives you the control necessary to safely manipulate and verify molecular changes in any laboratory setting.